Okay, great. Okay, so welcome back everyone to the afternoon session. And so E.G. Huang will continue with his mini course on convergence and conformal field theory.
Thank you very much. Sorry for the complication. So I already discussed the convergence for intertwining operators, product of intertwining operators, and also the Q traces or pseudo Q traces of product of intertwining operators. So these results basically these results are the foundation of the operator product expansion and modular invariance for the intertwining operators, and these in turn are the basic conjectures in the Moreau-Seiberg's paper. And using these results, using only the operator product expansion or associativity of intertwining operators, we actually proved we constructed a modular tensor category structure on the modules for the vertex algebra, both in the rational case and in the logarithmic case. For the modular invariance, a very interesting thing is that this convergence certainly will allow us to actually study the modular invariance, and the modular invariance actually in turn is needed in the proof of the rigidity of this braided tensor category. So it's quite interesting that the rigidity, it looks like a genus zero phenomenon, but see, actually the proof, one has to use this kind of Q traces and so on. So you actually have to use the Q traces of product of two intertwining operator. Only the Q traces of one intertwining operator is not enough. Okay, so this is quite important. And then see the proof is certainly in the rational case. Okay, in the rational case, we already constructed the modular tensor category. In the logarithmic case, C2 cofinite case, we actually already have the braided tensor category, but the rigidity and the modularity is still conjecture. At this moment, this is still not proved yet. So this is still conjecture. That is a C2 cofinite vertex algebra. It's a module category of finite length. Should be a rigid and satisfy this non-simple modularity. Okay, so this is still conjecture, but I hope. Okay, now I'm finishing the proof of non-simple modular invariance. I hope that this might help. Okay, so but see, still I do not know how to prove the rigidity, for example. Okay, now today what I want to discuss are the following. First of all, I will quickly discuss the convergence related to the solving of arbitrary Riemann surfaces with arbitrary local coordinates. Okay, so this is actually necessary if we want to construct conformal field theory in the sense of Gram-Segal, because Gram-Segal, he uses Riemann surfaces with arbitrary boundary parametrization, the boundary parametrization corresponding to arbitrary local coordinates. And also, it is necessary if we work with high genus theory, because for genus 0 and genus 1, basically we actually have some kind of standard local coordinate on the standard global coordinates on the genus 0 surface and the genus 1 surface. So we can choose some standard local coordinate, but on high genus Riemann surface, we do not have such canonical global coordinates. So you have to consider arbitrary local coordinates. So this is the first thing I want to do, but I will just discuss quickly. I will not get into any technical details. the second thing I want to discuss is just say that there is a results. So the for hygenus theory, I actually proposed the conjecture on the convergence in a hygenus theory, and then Bing Gui, he actually proved this conjecture. So I want to just discuss this result. And then, then there are two things I really want to discuss: the conjectures and the problems. So these are open problems, which if they are solved, I believe that it will lead to some really important progress. So the first is the orbifold conformal field theory. So here I'm talking about general orbifold conformal field theory, not some particular like cyclical group and so on. And the one of the main motivation is still this conjecture of the uniqueness of the Moonshine module by Frank Laplace-Merman. And then the second the problem I want to discuss are those convergence problem associated to the cohomology theory of vertex algebras. So in this cohomology theory, the cochains are defined to be something which must satisfy certain convergence conditions. So if you wanted to even calculate this cohomology, you have to determine all those things which satisfy this convergence condition. So we need to actually study all these convergence. So let me first, I think this is the fourth part. Okay, so this is the convergence related to the solving of the Riemann surface with arbitrary local coordinates. So let me just briefly discuss that the reason why we have to do this is because eventually we do want to construct. We wanted to actually prove that the vertex algebra representation theory give us a conformal field theory satisfy Siegel's axiom. You see, Siegel's axiom, he actually just he extracted these axioms from the path integral formalism. So if the path integral formalism is true, then you see definitely these axioms must be satisfied. So his formulation is this: the given sort of like you have a category of circles, and then you have morphisms given by Riemann surfaces. And then the conformal field theory is that given an object in this category, geometry category, you have to have a Hilbert space. But there are three circles, each circle corresponding to one Hilbert space. So it corresponding to this h tends to 3 and 2h. So for example, that a conformal field is a functor. So from this category to this category, and objects goes to objects, morphism goes to morphism. So associated to this sigma, there is some kind of a map, say like the nu of this sigma. Certainly, this can be taken to be the equivalence class, conformal equivalence class. So here, the main thing that in the geometrically, we have these arbitrary local coordinate parametrization. This can be general. So therefore, in particular, if we have, so for example, I will discuss only the simplest case. For the simplest case, if we have only one incoming, one outgoing boundary components, so it should be such a and we consider simplest case that this is genus 0. Then you see we have such a tube with two arbitrary parametrized boundary components, and this kind of Riemann surfaces, it corresponds to exactly the sphere with local coordinate here, it's 0, here it's infinity, and you have arbitrary local coordinate. So up to now, when I discuss this intertwining operator or vertex operator, these local coordinates are just the standard one, okay, the one which given by the global coordinates. But if you want to have arbitrary local coordinate, you have to have arbitrary boundary parameterization. You have to have arbitrary local coordinate. So you see, if you cut a disk around 0 and around infinity, you certainly get such a tube. So the main thing is that we actually want to actually starting with a vertex operator algebra or a module for a vertex operator algebra, we actually want to construct such a map. Okay, so like for each boundary circle, it should correspond to some kind of a module. Okay, one particular module, and then you see you will have to have such a map. Now, there is one complication in the theory of a vertex operator algebra is the following. In Siegel's formulation, he always used the Hilbert space. Okay, so for the Hilbert space, it's a complete space, and therefore, indeed, you can talk about it's a map the Hilbert space to the Hilbert space, but in the representation theory of vertex operator algebra, we only consider a graded space. And these graded spaces should be viewed as a dense subspace of a Hilbert space, or more generally, some nuclear topological vector space. So this is only a dense subspace. So you do not really expect that this definitely will not equal to its completion, topological completion. So see, the map, the image is not in the W usually. It will be in the algebraic completion I briefly mentioned before. So actually, it is because of this algebraic completion which created the problem of proving convergence. Another way of understanding this is also that, like if we want to construct the conformal field in the sense of Siegel, then maps must be trace class. So trace class again, you also have to prove convergence. So convergence is always an important problem. So now let's discuss the simplest convergence problem in this simple case. If we have only like a sphere with 2 punctures and 2 arbitrary local coordinates. Now for sphere with 2 punctures, the local coordinates, like what I draw here, the maps associated to this actually is given by the following. It is given by the just some exponential of, say, AJ, the LJ. This is the Virasoro operator. And then this J is positive, so it's in Z plus. And also there's 0, you actually have L0. This part corresponding to the arbitrary local coordinate here. Okay, so it corresponds to only local coordinate here. So roughly speaking, that the local coordinate here is given by actually a power series, right? It's a power series, and because local coordinate must vanish at 0, so it's a power series with the first term to be like A0 multiplied W. And you can always write this as exponentiation. I think it's there should be some kind of a minus or something. So the main thing that you can write this as something like the sigma, the AJ WJ plus 1 DDW, there A0 W DDW apply to W. So you can always write the arbitrary such an arbitrary form, the Laurent series in this way, and then you take these coefficients, you get this. So similarly at infinity, you can do the same thing. So you will get sigma B J, in this case L minus J. Okay, so you can do the same thing, but you just use the minus j. There will be no such term like L0 because you can always choose the local coordinate at infinity such that the first coefficient to be equal to 1 because we have SL2 C to SL2 C, you fix 2 puncture and then fix the local coordinate at infinity. So we do have such map. This map is indeed given a module. It is from a module to its algebraic completion because we have this infinite sum. Okay, so algebraic completion is just the direct product of homogeneous space, not a co-product. So it has infinite sum. So anyway, this is well defined. But see, the main complication that if we want to consider the composition of two geometric morphisms, if you have two of these things, you want to compose them. Okay, so here you have one operator. So for example, you call this this map to be phi1. So this is like a phi1, and you have another one is phi2. You wanted to actually compose them. Okay. Now, here this problem of convergence is the following. Because the phi1, phi2, they do not map to W. So they are from, this phi2 is from W to W bar, not from W to W. Okay. So therefore, when you compose, what do you mean? Okay, the only meaning is the following. You actually phi1, okay, then you take a projection to its homogeneous subspace of weight n, and then phi2 apply to some W. And then you take the sum, and in general in C because it's module, but certainly this is usually it's not. It has only finitely many congruence class of non-integers. So we have to consider such a sum, and then see the convergence problem is exactly that. Why this is convergent? Okay, so this is another convergence problem in this case. Okay, so this convergence problem is actually proved in the following way. So we see that for example, phi1 is given by this. Phi2 is also given by such an expression. So basically, phi1 composed with phi2, you can actually write this as E sigma. Okay, so let me just say that this is B1 because we do have two of these, and E sigma B. Sorry. This is A1 JLJ, and the A01 L0. And then you also have to compose with, so just to multiply E sigma B J2 L minus J, E sigma AJ AJ2 LJ A02 L0. So roughly speaking, this composition is just this. Certainly because of exponential, you will have an infinite sum. Okay, so we need to prove the convergence of this. So how do we prove this? It's the following. We actually have to use the geometry. The geometry is that when you sew these two together by identity boundary, or you just using the local coordinate, you can also cut disk, identify the boundary of disk. You actually, after you cut, you still get a genus zeros Riemann surface. And for genus zero Riemann surface, we have the uniformization theorem. So the uniformization theorem will actually say that it will corresponding to the standard way of writing down such a sphere, which is exactly using our pictures that you can always use this picture 0 to infinity, 0 infinity, and the local coordinate here. Okay. So, but see, the main thing that after you use the uniformization theorem, these local coordinate here at these two places depends on the local coordinate on phi on these two Riemann surfaces. So we actually have associated to this uniformized Riemann surface, Riemann sphere. We also have the exponentiation of something that we can call I can call this psi j, psi minus j. This is L minus j. And then here it's the E sigma psi plus j, L j, and then see the here it's a small psi L0. Okay, so this is after you do that, use the uniformization, you actually get this surface because these two surfaces are conformal equivalent. They should correspond to the same operator, so you get this. Okay. Now, these psi j and a small psi, this should be, I should write this as a capital. It doesn't matter. Okay, so these psi, they are actually functions of these b and a, bj and aj. They are functions of these things. So the main thing that one can actually use a theorem in complex analysis. There's a theorem by Grout. He actually using his theorem. So his theorem is something like if you have some kind of a family of complex manifolds, if for the requirement is that you only need to have a smooth family, and such that this family for each, you see, the family is certainly you have a parameter. This parameter is certainly a complex manifold, and then for each parameter, you have a fiber because it's a family. So you have some manifold, complex manifold. These, if for each parameter, these complex manifold, they are all the analytically diffeomorphic. Then you see this family must depend on the parameter holomorphically. So this is a very old theorem in complex analysis, complex manifold theory. So using this complex manifold theory, we can prove that these psi as a function of these a, b, and a small a, and so on are analytic. Okay, so this is first of all, these things are analytic. And also, on the other hand, you can directly, because we have a commutative formula for this Lj and L minus j. So using these commutative formulas, so here actually you can use the one can use the Campbell-Hausdorff formula. So you actually can write this again using some kind of a this kind of exponential. You can still write this as such an exponential. This is minus j, this is j, Lj, and phi 0. I think the L0. Okay, so you can write this, but there will be extra term. That's C gamma. What is the extra term? The geometrically, if you solve Riemann surface, there will be no central charge. Okay, but if you use the Virasoro algebra, there will be central charge. The central charge will actually give you such a thing. So now, if you do this, you actually only get these phi, capital phi, small phi, and this gamma. They are all series. They are not functions. They are series. Okay, so the main thing that you have to prove that all these series are convergent. Okay, so the proof goes this way. Because these psi are convergent, psi are analytic function from geometry. So then you see what we do is that we, because they are analytic, so you can expand them as a series. And then one can show that the expansion of these psi are exactly equal to these phi. Okay, so expansion of psi are series. These series are equal to these phi. Therefore, these phi as series, they are convergent. Okay. And how do you prove the gamma is convergent? Okay, this is slightly more complicated. The gamma is corresponding to the central charge, and central charge is really described by the determined line bundle over the modular space. So here we have to use the determined line. So I will not get into detail. The main thing that we can actually construct the determined line for every Riemann surface with parameterized boundaries, and then we can prove that this determined line, they depend on the determined line bundle depend on the modular space of a sphere with puncture and local coordinates analytically. Okay, so it depends on these analytically, but not just the bundle is holomorphic. Also, when we do the sewing operation, the determined line also can be sewn together to actually have a canonical map between the different determined lines on different surfaces. These canonical isomorphisms, they are also analytic. Okay, so using the analyticity of the canonical isomorphism for the determined line bundle, for the canonical isomorphism for determined line, we actually have some kind of analytic function, and then the analytic function can be expanded as series. You can prove that the series is exactly equal to this gamma, and therefore this gamma is convergent to that corresponding the canonical isomorphism for determined line. So in this way, we prove this is convergent. So if all the series are convergent, then see here the original series is convergent, because the original, it's a series. This series, using the Campbell-Hausdorff formula, you only get still get a series, but the series is actually the same. So this series and this series and this series are actually same, because this is convergent, so the original is convergent. So this is the convergence for general the local coordinates. So it is actually necessary for us to do this. So this is the first convergence I want to discuss today. Then another convergence, which is actually important progress, is a high genus. Convergence results. So this is proved by Bing Gui. So I think he proved this in 2020. Okay, so the roughly speaking, let me just discuss the problem. The problem is the following. Okay, so for example, we already discussed the trace. So let's say actually his result is only for the rational theory. So we only take the trace. We do not have to take the pseudo trace. So I already discussed that if we have two intertwining operator, we can actually take this Q trace So this is a convergent, and actually this also satisfies the modular invariance, but under suitable condition. In the rational case, it should be C2 cofinite, and then all the modules are completely reducible, and there's a minor condition on the weight of elements in the in the vertex operator. So if this is already proved to be convergent. Okay, and then you see you can further. So the main thing that if in the case that the W1 here is this is belong to W1 and this belong to W2. Okay, so say for example, if W2 is equal to W1 prime. It's a great deal. Then you see, we can actually further take a trace of these two places, right? So the W1 you put, for W1 you put a basis, and then for W2 you put a dual basis, and then you take the sum. So this is another trace. Okay, so this trace will corresponding to a genus 2 Riemann surface. So here, if you want to study such high genus theory, you have to first prove this convergence. So this is another convergence one has to prove. Now, actually, I want to say that for high genus, actually the only problem we actually need to prove is this convergence. You see, for genus 1, we have to prove the associativity, which is one of the fundamental thing we have to prove. And for genus 0, right? For genus 1, we have to prove modular invariance. Okay, so both associativity and the modular invariance in these two cases, they correspond to the associativity is something like if you decompose a Riemann surface in two different ways, Riemann sphere in two different ways, you can use intertwining operator to construct the corresponding correlation function. You have to show that these two different ways actually give you the same space of correlation function. So that space is what people call the conformal blocks. So the space of conformal blocks should be the same. So you have two different ways of decompose sphere with punctures and local coordinates. Then the corresponding algebraic results is that these two ways give you the same thing. That's the associativity. And the modular invariance is also the same, is also have the same interpretation. This kind of a Q trace is one way to construct a torus. And then the same torus can be constructed in different ways. So for different way of constructing the torus, as long as the torus are conformally equivalent, they should give you the same thing. So we need to prove a modular invariance. And then see the main thing that in the Riemann surface theory, we have the theorem says that in general, we have arbitrary Riemann surface. So you also have all different decomposition into these the basic ones, like the sphere with 3 punctures corresponding to intertwining operator. There are many different ways, but these different ways. So the main thing that different decomposition, the change of these decomposition corresponding to an action of the so-called mapping class group. So but see there's a theorem says that these different way of decomposition, they are connected by just locally you can cut pieces of the surface locally. Either the change is given by the change corresponding to associativity, or the change given by the change corresponding to the modular invariance. So from the geometrical point of view, as long as you have proved the genus 0 and the genus 1, there's associativity and modular invariance, the high genus thing, the mapping class group action under the mapping class group action, it is also invariant. Okay, but see so this is okay. I should say that this is the reason why. Okay, after we constructed the genus 0 and the genus 1 modular functor, then you can use genus 0 and the genus 1 modular functor to construct high genus modular functor. So this is something that genus 0, genus 1 already gave you the high genus modular functor. So if you want to construct, so for example, if we are only concerned about the modular functor, then see the associativity of intertwining operator plus the modular invariance of intertwining operator, it's enough. Okay, so after these two things are proved, so that's the reason why we actually get to the modular tensor category. And the modular tensor category is equivalent to modular functor. So indeed, modular functor is for high genus. But you see, if we want to construct conformal field theory, which is more than just the modular functor is not really the conformal field theory. To construct conformal field theory, we still need to make sure that these traces are actually well defined. So the convergence problem become the main problem, because if you can prove that these are actually the convergent, then you see basically if you want to prove that a different way of taking several traces to obtain high genus surface, they must give the same vector space, because you can reduce this to genus 0 and genus 1. So that's the reason why in the high genus case, we actually mainly only want to prove this convergence result. Okay, so then you see I actually proposed this as a conjecture, because at that time, so the main difficulty in proving this is that in the genus 0 case, the associativity of intertwining operator, and in the genus 1 case, that's the pseudo trace. If you just remember, when I write down, see, I didn't write a proof, but I write down formulas, right? So I say that from these formulas, you can derive differential equation. These formula, you see that these formula, we all have these rational functions. Okay, so these rational function, like for the Q trace, we actually have to start with intertwining operator. Intertwining operator, the Jacobi identity or whatever, the actually involving the genus 0 meromorphic functions. These are like for two intertwining operator, we do not have Jacobi identity. But see, in the definition of intertwining operator, we have a vertex operator multiply intertwining operator. These do have Jacobi identity, or the product is convergent to some function which actually the singularity for like a z1 minus z2 equal to 0 is actually a pole. So we do have some meromorphic function on a sphere. Okay, and then see the formula I wrote down the last time for pseudo trace or trace. These are the coefficients are meromorphic functions on the genus 1 surface. So the proof of these formula actually have to use the Q expansion of the Weierstrass P function. And the Q expansion of Weierstrass P function in this picture, in the conformal field theoretic picture, is nothing but a decomposition of meromorphic functions on genus 1 surface into meromorphic function on genus 0 surface. So actually, there is a sort of very nice interpretation of this Q expansion that says that Q expansion of the Weierstrass P function is nothing but a sewing formula for the meromorphic function on the genus 1 surface. So the Weierstrass P function on meromorphic function on genus 1 surface. So you can using the sewing operation to obtain this meromorphic function from meromorphic function on genus 0 surface. So this is essentially the one of the main thing we need to use. Okay, so for high genus, the main thing that actually see, I do not really know such decomposition of functions on high genus surface into the meromorphic function on the low genus surface. So I actually, at that time, I proposed this as a conjecture. And then see, Bingui actually is very interested in this problem. He actually find that there's actually also an older theorem by Grout. He actually indeed had this type of decomposition, even though it's not written in the way that I am used to. But see, it indeed means something like this. So using this, okay, then he can prove that this is convergent. Okay, so certainly his proof is only for rational theory. It means that it should satisfy the three conditions in my theorem on the modular tensor category and so on. So this is high genus convergence is proved. And therefore, in particular, the high genus modular invariance, or CDO, we usually probably should not call the modular invariance. It's the invariance under the action of the mapping class group follows from the modular invariance and the associativity, and therefore this kind of double trace. So here's we take the trace here and also take the this trace. This kind of double trace will define a correlation function on the modular space, not on the Teichmüller space. See, if you still have some particular trace like this, this is still defined only on the Teichmüller space. So because it's the invariant under the action of the mapping class group, and therefore it's defined on the modular space. So this is a very nice result. And then see the main thing that for rational conformal field theory, because of all these genus 0, genus 1, and this high genus convergence results, so essentially, okay, I should only say essentially, the problem of constructing conformal field theory in the Siegel sense essentially is known. Okay, the only thing that we still actually are working on this is that in our theory, these modules are graded space, as I explained. These are all still graded space, not Hilbert space or nice topological vector space. So we actually need to take the completion to make sure that all these things work for this completion. This will involve actually some subtle analytical results, because we need to actually further prove some analyticity, and so that when you have the topological completion of this module, these a lot of elements will enter into that. So how do you prove that these things are in our topological completion? One has to use this kind of analyticity. So this is still the under the progress. We are still working on this. Okay. So now, so this is the high genus convergence part has been proved. So now I wanted to discuss really the open problems. So this is 6 is the orbifold theory. Okay. Now, orbifold theory, roughly speaking, is the following. Okay, so the given, so here you can actually talk about orbifold theory in the conformal field theory sense, but see, because we are discussing this using the representation theory of vertex algebra, so I will discuss from this point of view. Basically, we actually view conformal field theory just as the representation theory of a vertex algebra. So assume that we already have a nice conformal field theory, say for example rational one. So we have a nice vertex algebra, and then we have a group of automorphisms. So this is a subgroup of the automorphism group of V, and then see the main thing that if this V give us a nice conformal field theory, we actually want to construct a conformal field theory associated to the fixed point subalgebra. Okay, so that's basically that's the orbifold theory is about. Okay, you want to look at the fixed point and then see the construct theory. Now, the main difficulty is the following, because I already proved the theorem that if V satisfy, like say for example the 3 conditions, C2 cofinite, computed disability, and so on, then see we can construct everything, all these modular functor, and now see even high genus convergence is approved. So modular tensor category, even in the formula, everything can be proved. Okay, So a natural way of just thinking about the orthogonal theory is just to try to prove these property for the fixed point subalgebra. Okay, so this is certainly a natural thing to do. And actually this is indeed Carnahan and Miyamoto, they indeed obtain nice results. So what they did is that in the case that G is a finite cyclic, it's a finite cyclic group, and they actually proved that this subalgebra is indeed satisfy the same condition as we start with. Okay, so this is their result, and then recently there's a different proof by McRae. So this is a nice result, but unfortunately, if G is a finite cyclic, you can generalize this too. If you repeatedly using this result, you can generalize this to G to be solvable. Okay, solvable certainly works. But see, the for the study of conformal field theory, actually, we are actually interested in, for example, we are interested in the master, which is a simple group, and then see the which is a non-abelian simple group, and then see the we are interested in all these like a 26 sporadic group, and so solvable group is not the correct class of group we should work with. So see the main thing that we want to prove this kind of results for more general type of group, but this type of proof is extremely difficult. So basically, this proof of this satisfy these conditions, one has to use all the existing theory of this vertex algebra construction of the conformal field theory. So I myself think that probably, see, this is certainly my own strategy. Probably we should not, I should say the main difficulty, certainly the C2 confinement is also not easy in general, but see the main difficulty is that for the computer-reducibility. Okay, so if this start with some vertex algebra whose modules are computer-reducible, you want to prove the subalgebra also whose modules are computer-reducible. This is very difficult. And so I think that probably, so the finite cyclic is also already so difficult that you have to use the whole theory of whole representation theory results we obtained up to now. So see, I'm thinking that probably we should not directly prove this is the subalgebra satisfy these property. Instead, we should just work with the original algebra. And also we do not have to always work with computer-reducible case. We can work with the logarithm case. And then see the after you work out the logarithm case is certainly more general. After you work out all these results, then you look at the computer-reducibility. So the idea is actually agree with a lot of study in physics that is, or in mathematics, that is instead of try to look at this, we actually still look at V, but we have to study twisted modules. So we do not work with VG modules, we work with twisted modules. And we have to work with so-called twisted intertwining operator. So here, by twisted intertwining operator, it is nothing but the intertwining operator among twisted modules. So that's the meaning of this. Okay, so this is what we really I would like to study, because the reason why this looks relatively easier is that we still work with V, not with VG. VG is difficult, so we do not know how to go to the subalgebra. But this is still work with V, but it's more complicated. Before we always work with module. Now we work with twisted module. So twisted module is certainly more complicated, but at least it's analogs to modules. So we can immediately have all these conjectures, which are in parallel with the results we obtain. So here's the first conjecture. Okay. So here, because I do not have a lot of time, so I will not describe the detailed definition of twisted module and twisted intertwining operator. So let me just formulate the conjecture. So actually, I have these papers about these conjectures, so you can look at them. So the conjecture is the following: if V satisfy okay, let me just say the three conditions. So I would just say this. So the three conditions that for rational conformal theory. So these there are three conditions for which we get rational conformal theory. So the three conditions that is that the vertex algebra must have only non-negative weight state, and the weight 0 must be proportional to the vacuum, and the vertex algebra as a module for itself shall be equivalent to its graded dual, and also it shall be C2 cofinite, and all the relevant modules shall be computer-reducible. And also another condition that G is finite. G is a finite group. Then the twisted intertwining operator satisfies okay, so let me just first say the following: satisfy the associativity. So the main thing certainly I want to discuss is the convergence, but see when we write on these, already we have the convergence as a conjecture. Okay, so this is the conjecture that see I discussed for intertwining operator. We actually proved that the intertwining operators do satisfy the associativity and the modular invariance. But see now we actually conjecture that if we have a nice conformal nice vertex algebra and G is finite, then you look at, so here the main thing that this should be G twisted. Every module, sorry, I do not have to say this because it's for module. Here I'm just discuss the intertwining operator. But these intertwining operators are among, they are among twisted module, but these twisted are twisted but only by elements in this G. Okay, so the main thing that for the untwisted case, we already have the theorem, so it's very natural that we should have this theorem. Okay, the main thing that this conjecture now, if you use the results of Kanahan Miyamoto's and then see in this finite cyclic and a solvable case, we can actually have this result. But in general, this is we do not have any results. Okay, for the if it's not like a finite cyclic essentially, so there's no such result. So especially the difficulty, the main especially difficult part is that when the group is non-commutative, because cyclic group is commutative. So when the group is non-commutative, you might have two twisted modules which are twisted by two elements in the group which are not commute with each other. This is especially difficult. And the reason why this is still conjecture, I do not know how to prove this yet. I should say that when we discuss associativity, first we have to have the convergence. Okay, and also for the modular invariance, we also have to have the convergence. So even the convergence, I do not know how to prove. The main difficulty is the following. Just remember when I derive these differential equation, I have to use these formulas. Write down some formula for the product intertwining operator or Q trace. These formula actually you have to use the some identity for vertex operator acting on modules, and these vertex operator acting on modules are always contain only integral power of the variable, so it's very easy to deal with. But for twisted module, okay, in general, the vertex operator also contain non-integral power and also logarithm in general. If the group element is not of finite order, certainly see when G is finite, every group element is finite. Therefore, we do not have logarithm. But see in the most general case, so this is a conjecture. Then see the more general problem is for the more general group. So the twisted vertex operator also contain these multi-valued thing, and this makes the derivation of the formula become really difficult. Actually, in the case that all the group is abelian, actually I actually tried, but there's one thing is that there's one thing that I will get the infinite sum. So in the formula I wrote down before for associativity, there are only finite many terms, but I get infinite term. So I believe that there should be a theorem which says that I have these three conditions. Say, for example, C2 cofiniteness. I believe that C2 cofiniteness will actually sort of reduce this infinite sum to finite sum. So a lot of these infinite many terms will have a lot of zeros. But at this moment, I still do not know how to prove this. So this is really a conjecture. And then we have the general problem. Okay, if V is C2 cofinite, so I think that so probably like a C1 cofinite. So actually, I should not say V is C1 cofinite. It's a V module should be C1 because V the algebra is always C1 cofinite. And G, the not finite. Do we still have? The say for example associativity, because associativity only needed C1 cofinite. So this is a problem, and I myself think that for the most general type of a group, so for finite group, this might be this probably is true, but for not finite, I think that probably we need some kind of a more condition. So so the problem is that find conditions. So similarly for this modular invariance. Okay. So certainly these involve not just associativity but also convergence, because if you want to talk about convergence, modular invariance, and associativity, we have to first prove convergence. So this is a more general type of problem. So the main thing that one has to find some conditions so that under these conditions, like on the group or on the algebra or on the modules, under these conditions, we do have all these associativity and modular invariance and so on. So let me just say why I think that this is important, because if we can do these things, then basically we can use these. Okay, so I actually prove a theorem. A theorem I proved is the following: any VG module, which is a sub algebra, for V, which is the fixed point subalgebra, VG module is always contained in some V twisted module. Sorry, it should be twisted V module. So every VG module is always contained in some twisted V module. And therefore, you see, if we have a nice theory of these twisted V module, then see we can actually take some particular subspace, whatever, to obtain VG module. And therefore, we will actually obtain all the results on VG module. Eventually, we get the original orbifold theory. Okay, so this is the idea. Okay, so because the twisted module, at least for conjecture, it's much easier to conjecture than VG module, because it's everything supposed to be analogs. And one reason why this kind of strategy might be useful is the following: is that for vertex algebra, for this moonshine, the uniqueness of a moonshine. Moonshine module. Okay, the uniqueness of moonshine module says that if you have a vertex algebra, satisfy three conditions. So the first condition that the central charge must be equal to 24. Oh, I think the I forgot to charge my iPad. So but for this point, I can just have a discussion. I can use the file of my paper. So maybe I will just use the file of my paper to actually discuss this, because I already typed down these things. So let me see. Okay, yeah. So okay, so that's fine, because this part I do not need to write down a lot. So let me share my the file of my paper. So this way. Okay.
Okay. Yep, we're seeing it here.
Yeah. Okay. So the actually for the you see, this is the paper I'm preparing. So actually, this is more precise. I have a more precise the conjecture here. Okay, because I do not need to see the I when type I have more time to type. So the main thing is that so the first part is this conjecture 7.1 is about the associativity. Okay, so associativity, so it's similar to the case of untwisted one, and then this conjecture 7.2 is specifically for the modular invariance. Okay, so now here the main thing that before I go on to the next point is I do want to discuss okay, I think it's very nice that I can actually write here. actually I can write on this document. Okay, so that's very nice. Yeah, so see there, I can actually write. Okay, so let me say the following. So the main thing I want to discuss before I go to the next topic is that for the moonshine module, if we have a vertex algebra satisfy 3 conditions when the center charge equal to 24, and there's no weight to one element, and the other condition is that the only irreducible module for this vertex algebra is itself. Okay, if we have 3 conditions, vertex algebra satisfy 3 conditions, then it must be isomorphic to the moonshine module. This is the uniqueness of vertex algebra, the moonshine module. So this uniqueness is obtained by analogy with the Leech lattice uniqueness, because there's an analogy between lattice and vertex algebra. So for Leech lattice, it is a lattice also satisfy these 3 conditions. Okay, so there's also corresponding 3 conditions satisfied, and then see there's a proof by different people. I think the Conway has a proof, and then other people also give a proof. The Leech lattice, any lattice satisfy the corresponding 3 conditions must be equal to isomorphic to the Leech lattice. The proof is this, because lattice has a nice property, is that it can be embedded in the Euclidean space. So if you have a lattice in the Euclidean space, you can use Euclidean space to enlarge your lattice. You can actually construct an extra structure from this lattice, and then use this extra structure, you can prove the uniqueness. Now, for the vertex algebra, if you have an arbitrary vertex algebra, we do not have something you embedded sort of immediately. We have something you can put in the vertex algebra in this structure, which has the similar type of property. See, the Euclidean space and the lattice has a similar property. They are all abelian group, and so they all have inner products, and so we do not have such thing. So if we want to sort of prove the uniqueness using some analogy with Leech lattice, we have to see that whether we can find a larger structure which contain the original vertex algebra as a substructure. So if this orbifold theory can be developed, then see what we can do is the following. You start with such a vertex operator algebra, okay, and then you consider, say, for example, the 4 automorphism group, which is the 4 one, and then you just study all the modules for this VG. This is indeed sort of the largest structure for which V is a substructure. It's not the VG give us the larger structure. It's all the modules for VG give a structure which contain V as a substructure. So then see, the basically you have to consider all the modules, and you have to consider all the intertwining operators between these modules. So then you see the V is contained in this huge structure. Maybe I call this W. So we can actually enlarge the vertex algebra into this larger structure, and then you see we can actually probably use some kind of technique. So that's the one of the main motivation for this, at least mathematically, for this developing this general orbifold theory. So one should notice that if we have a usual vertex algebra, the vertex algebra we have discussed in the last 2 lectures, then see we always consider all the modules and intertwining operator among them. So this is already a larger structure than the original vertex algebra. So this is the reason why representation theory of vertex algebra give us a really nice structure. So all these modular tensor category and so on, it comes out of this. But in this kind of a particular case, V is the only irreducible module is V itself. Okay, so if you consider module, you will not really go beyond V itself. It's still V. So you cannot enlarge V just by adding modules. No, you do not get a larger structure. So that's why orbifold theory is the one that indeed you can actually get a very, very large theory. Like, for example, if the group is the monster, then certainly it's a huge group. You can get a lot of modules. Okay, so this is the one of the. Okay, I hope that this can be developed, and then after it's well developed, this whole representation theory. But to develop this kind of representation theory, we actually have to use the Twiston module, and then because every VG module is contained in some Twiston module, so we can use Twiston module to study VG module, to study things here. Okay, so that's the one of the main motivation for this whole general orbifold theory. Okay, so okay, now the last thing I want to discuss is this convergence problem in the cohomology theory of vertex algebras. So, so see for this theory, I think that it's basically the idea is the following: in any kind of representation theory, so we always have two important sort of basic thing and also tools. One is the tensor category theory. So that in some sense that representation theory, you just want to construct the tensor category structure, satisfy all the possible properties of this tensor category, and then see if you can reconstruct the original algebra you start with, then this category sort of is the correct category for the original algebra. So for vertex algebra, braided or modular tensor category or braided tensor category are not really the correct tensor category because they cannot reconstruct vertex algebra. I think that one can only construct like some kind of a quasi-half algebra or something. But when we construct these braided tensor category, modular tensor category, we actually construct some stronger category called the vertex tensor category, which depend on sphere with punctures and local coordinates. So I believe that we conjecture that these vertex tensor category can be used to reconstruct the vertex algebra. So this is the category side of the story for vertex algebra. But see in all the representation theory and in other part of mathematics, another important theory is certainly the cohomology. We need a cohomology to study a lot of things. So for example, even the computerizability can be studied using cohomology theory. And also when you consider extensions, deformations, we all need cohomology theory. So I myself actually introduced a cohomology for such vertex algebra. But see for this cohomology theory, I do not need the Verasura. Okay, so that's the reason why this is for so-called grading restricted vertex algebra. So we do not need the conformal element. Then see the main thing is the following. So let me just say that the cochain. So the main thing that the cochain. So the one, I think that for many years people actually have difficulty to construct the cohomology theory. There are a lot of attempts and there are even papers, but unfortunately these are not the correct cohomology for vertex algebra. The reason is that usually how do you construct a cohomology theory? You will consider maps from the cochains, maps from V tensor to the nth power and then to a module W, right? So that's the usual way. You always consider cochain to be such a map, probably satisfies certain condition, and then you can define the co-boundary operation. So for vertex operator, if you try to do this, it does not really work. So the main difference is that the cochain, we have to, it's still from the tensor power of V, but it will map to, instead of the module, it should map to so-called what I call the W bar valued rational function. So I use this to denote. Because it's a rational function, so I indicated a variable, which are Z1 up to Zn. So what are these things? These things are elements in this are you can write this as some function of Z1 to Zn, but it's valued in W bar. W bar is the direct product. It's direct. Sorry, it's not the direct product. It's the it's a direct product. It's not a direct co-product. W, and so it allowed the infinite sum. So we have to actually consider function valued here, such that if you take any W prime, which is in the graded dual, and this F, this will be an rational function in Z1, Zn. So this is the space. Okay, the space consists of all these F. So this is actually the necessary thing to do to actually introduce this homology theory. Okay, so we actually, these are the maps, and the cochain and cochain are such maps satisfy additional condition. Okay, and among these additional condition is that because on this module W and on V, we all have vertex operator. So you should be able to, so among these things is that we have to be able to multiply or compose the vertex operator with this map, So here, see the main thing that just to remember, our vertex operator, either you write the image like a V tensor V to V, like you'd write this as a formal series, or you have to write this as a map from like a V tensor V to V bar, which is algebraic completion. If you fix some Z, okay, when you fix some Z, Y dot Z here, fix Z, then it will be infinite sum, because this is an infinite sum. So when you compose with vertex operator, you actually compose with element in V bar, which is not in V. So you have to like project to the homogeneous subspace and then take sum. So you have to assume these are convergent. So one of the property when we discuss the cochain is that we actually have to assume that these maps can be composed with vertex operators. It means that these compositions are convergent. Okay, if they are not convergent, then it will not work. So everything works. So I can define co-boundary. So I will now write this down, and I can just the proof all the usual property the cohomology theory must satisfy. So this is very nice. These are like a deformation, infinitesimal deformation, square zero extension, and so on. But if you want to calculate the cohomology, we have to determine all those maps. So see here I give, see that in this part I give a example that is a two cochain. Okay, so here is the two cochain. A two cochain actually correspond to such map. Okay, certainly the original definition is not such a map, but so you can show that two cochains corresponding to such a map, which look like look similar to like a vertex operator map, but it does not satisfy the property for vertex operator. So if we have such a map, satisfy some additional condition, including one condition that you have to make sure that these composition, the product of this map with these vertex operator, they should be convergent. Okay, so this is the kind of a convergence condition I need. The reason why I need this to be convergent, and they should also be convergent to rational function. Now, why we need this? Because the co-boundary operation need this kind of a composition. Okay, co-boundary, without this kind of a convergence, I cannot define co-boundary operator. And therefore, see the if you wanted to calculate the like a second cohomology, you have to find all those maps such that these things are convergent. So this is not easy. So when you even for some simple vertex operator like a SL2 affine algebra, this is not easy to calculate. So one of the problem, okay, is this. So we want to know whether there's a general method that can be used to determine all these cochains. And also, I believe that there should be conditions. So we want to find some algebraic condition of V and W such that we can determine all the cochains using these conditions. So this is a problem I do not really know. I don't have any idea. Okay, so if we can do this, then we can calculate the cohomology of a lot of these things, a lot of vertex operators. Okay, now the last convergence problem I want to discuss is the following: is that in a joint paper of Chi and myself, we actually proved that if the first cohomology of vertex algebra is actually equal to so-called the space, what we call zero derivative. Actually, we proved that the first cohomology is isomorphic to the space of derivations with modular the inner derivations. This is a sort of, in some sense, similar to the associative algebra. And then we prove that if the first cohomology is equal to the space of so-called zero mode, there is a zero mode derivation. There's some derivation can be constructed from some zero mode operator. And then see that these gives us some derivation. So if the zero mode derivation, the space of zero mode derivation modular inner derivations is equal to this first cohomology, then we prove that any modules is completely reducible. Okay, so this is very nice, but there's another condition. See that if only the first cohomology have this property, we have a complete reducibility, then it will be very nice. But we actually have another condition. The first cohomology should equal to the space of zero mode derivations, but also we need a so-called composability condition. So we call this composability condition on modules. Okay, so but what is this composability condition? It is nothing but a convergence condition. So this composability is nothing but if you have a module and then you have a submodule. So you have a module and a submodule. And assume that you can, in this case, you can always find some W1 such that the direct sum is equal to, but this W1 in general is not a submodule. So you can just find W1 such that this is a direct sum. And if you can find such a W1 such that this product, see that here, all the other parts, this part, all the other parts are actually the, so all these parts are just the vertex operator on the modules. But this point is the first you project to W1, then multiply the vertex operator, and then project to W2. This type of thing are not vertex operator anymore. These do not, in general, because W1 is not module. So it's not even an intertwining operator. So if you can find such W1 such that this is a convergence, okay, then see, we say that this condition is satisfied. In the special case, if the original vertex operator has a subalgebra, has a very nice subalgebra, then we can prove indeed we can find such W1. Okay, but in general we have no idea, and therefore we have this problem, the last problem, open problem, that is, are there any algebraic condition on V, W, and W2 such that this convergence condition are satisfied? So I believe that if these convergences are proved, we can actually have a really nice, powerful theory of cohomology. Okay, so I stop here. So.
Okay, so let's listen to the speaker.
Thank you.
Are there any questions? Well, so I guess I might ask a question. So I wonder if, could you comment whether, you know, of any link between this cohomology theory and the chiral homology theory of Berlitz and Drinfeld?
Yeah, so I think that the difference is that their cohomology is for much more general vertex algebra. Okay, and therefore, see, for a lot of applications, see, I should emphasize that for all the theory, representation theory of vertex algebra, our vertex algebra structure, like the grading and so on, especially like the grading restriction condition, low boundedness, play a really important role. So if there's no grading condition, we almost no really substantial theorem can be proved. So for the cohomology theory, I think it's the same thing. I think that I actually wrote a paper jointly with Lapasi, proved the equivalence between Berlitz and Drinfeld's chiral algebra and the vertex algebra. But this vertex algebra is general. There's even no grading and so on. So I think that, okay, I think that their theory, their cohomology theory is mainly for this is kind of a general thing. So it works for this general thing, but we actually wanted this to be more specific, satisfy these more restrictive condition. And this is really important because, for example, for deformation, we do not want to deform the vertex algebra to a more general vertex algebra. We want to still restrict it in the same category, because otherwise we do not get these vertex algebra which give us the nice result. So that's what my understanding is.
Right. Also, somehow their construction involves a choice of algebraic curve, right? I wanted to. Oh yeah, I just wanted to ask because so recently myself and Reimundo Heluani found a way to construct classes in chiral homology of tori using derivations of vertex algebra with values in a module, which I see is exactly the same. It's what appears also in your cohomology theory here.
I see.
So
okay.
That's what made me interested what relation, if any. But of course, there's no elliptic curve in this in your picture. So
yeah, I see. My picture is still used only genus zero surface. You see the space I consider is the W bar value, the rational functions only. So I see, I do not really know, but see probably one can consider meromorphic functions are general Riemann surface, one can just try to see whether this come out, but I do not know. I only this is the cohomology theory only associate to, essentially only associate to this sort of like the product in the vertex operator. The product is given by the vertex operator map. So like for example, the second cohomology, it's infinitesimal deformation of the vertex operator map, basically. So that's what's going on. But see, if you go to the hygenous surface, then see definitely it should correspond to some, say for example, hygenous deformation or something. I do not know. Yeah, I have no idea. So that would be very interesting if you actually can do this.
Oh, okay. Other questions? Let me just see if there's anyone on Zoom wanting to ask a question. Oh, looks like no. Okay, so then let's thank the speaker again for a very interesting series of lectures.
Hey, thank you very much.
Okay. Okay, so here, right now it's tea break. I think there's cake as well. So, and we resume at 3 o'clock.